Okay. So the first mini talk of the okay, guys, please. So the first mini talk of the conference by Johnston and okay. Samuel Johnston from University of Bath. So thanks for coming. And the talk is about bead processes, superstation, and continuous Kasteleyn theory. Okay.
Okay. So thanks to Moshe and Kadina for the chance to speak. So I'm going to be talking about bead processes today. So what is a bead process? So a bead process is a collection of points lying on a bunch of strings running in parallel, with the property that the points on each string interlace the points on the neighbouring string. So this means that whenever you have two consecutive beads on the same string, and you look on the neighbouring string, there's a point between them. So we say that points on neighbouring strings interlace. Now, this interlacing phenomenon is ubiquitous across mathematics. If you take a polynomial with n real roots and you look at the roots of its derivative, they will sit between the roots of the original polynomial. If you take a Hermitian matrix with its n real eigenvalues, then you look at the eigenvalues of an n-1 by n-1 minor of this matrix. The eigenvalues of the minor will again sit between the eigenvalues of the original matrix. There's even strong numerical evidence connecting bead processes with the zeros of the Riemann zeta function. If you take a giant bead process with tons of strings and tons of beads on each string, and you choose one randomly in some suitable sense, and you look at the behavior of the beads along one given string, they tend to sort of gently repel one another. So the beads don't like to lie too close to one another. There's a bit of repulsion between them. If you look at the zeros, the non-trivial zeros of the Riemann zeta function, they seem to exhibit the same sort of repulsion. There's extremely strong numerical evidence that this is true, and some sort of tentative evidence on this front in the number theory literature. And we'll be particularly interested today in the volumes of bead processes, so I'll be a bit more specific. Suppose I have n unit-length strings running in parallel with one another, and on each of these strings I have k beads. And these beads have to interlace the beads on the neighbouring strings. So this creates, if I label these points with the array of numbers Tij, this creates a sort of complicated set of inequalities that these Tij have to satisfy. Now, this array of real numbers between 0 and 1 can be thought of as an element in the unit cube in nk dimensions. I have n strings, k beads on each string, and each of these beads, each position of the bead corresponds to a number between 0 and 1, and therefore I associate the configuration with a vector, and I ask, what is the volume of this subset of the unit cube in nk dimensions corresponding to the set of bead configurations on n unit length strings with k beads on each string? Now, if you get a pen and paper out and start fiddling around with these configurations and trying to tackle this problem by elementary means, you'll find that it all soon spirals out of hand really quickly. It seems impossible to tackle this problem just using some sort of elementary argument, perhaps with induction on n or k. So it turns out we need to appeal to something more sophisticated. So there's some evidence about the way that bead configuration volumes behave macroscopically. So this evidence occurs in the setting of Gelfand-Settman patterns. So a Gelfand-Settman pattern is a triangular bead configuration. We have n strings here. We have n beads on the bottom string, n-1 on the next string up, all the way up to 1 bead on the top string. Now, if I fix a bottom row for a Gelfand-Settman pattern, so I've fixed n real numbers, I can consider the set of ways of completing this pattern. So I can write GT lambda 1 up to lambda n for the set of real numbers Tij that complete this pattern. So it's a set of real numbers satisfying a complicated set of inequalities. Of course, this set of real numbers is a compact subset of r to the n times n minus 1 over 2. Now, since this is a compact subset of r to the n times n minus 1 over 2, we can talk about sampling an element uniformly from this subset. Or in other words, we can talk about a uniformly chosen Gelfand-Settler pattern with a fixed bottom row. So a natural question to ask at this stage is...
compact?
Yeah. So it's compact. A simple way of seeing it is each one of these Tij has to take a value between lambda 1 and lambda n.
Oh, those are fixed.
Yeah, those are fixed, yes.
Oh, yeah.
Sorry, yeah. So for each fixed choice of lambda 1 up to lambda n, it's compact. Yeah, thanks. So we want to study random patterns that are chosen uniformly from the set of patterns with a fixed bottom row, lambda 1 up to lambda n. And the natural question to ask is, how do these patterns behave macroscopically when we send the number of beads along the bottom row to infinity according to a certain density? So suppose I have tons of beads along the bottom row, and there's a certain density of these beads. How does the pattern behave? What's the overall shape of the pattern? So here's a simulation. You'll see that the beads higher up in the pattern sort of space themselves out in an efficient way so as to make room for all of their bead friends elsewhere in the pattern. Now, there's another way of visualizing these patterns in terms of these sort of surfaces.
Do you have a direct sampling algorithm for this?
I was joking when I said it's a simulation. It's just a drawing I drew with my iPad. Sorry. So to each one of these Gelfand-Settler patterns, we can associate a surface as follows. We take our n beads along the bottom row, and we draw n spikes along the sort of diagonal of the lattice. Vertical spikes where the height of each spike corresponds to the position of each bead along the bottom row. And we can do this with the beads on the next string up, on the next diagonal. And we can do this with the whole pattern. So we've associated our pattern here bijectively with a bunch of spikes. Again, each spike in the pattern has a height that corresponds to the position of the bead. Now, I can linearly interpolate between these spikes, and I create a random function. Of course, I've fixed the bottom row of this pattern, but the beads on the higher rows are random. So this is the same as fixing the diagonal height of this function, and but allowing the rest of the surface to sort of fluctuate randomly. Now, it turns out that when we look at these surfaces, and the number of beads along the bottom row is very large, it appears these surfaces behave in such a way, they almost behave deterministically on a macroscopic level. So Shlyakhtenko and Tao, in some recent work in the setting of free probability, which is an abstract area of probability connected with operator algebras, studied what can be understood in some sense as continuous analogues of Gelfand-Settler patterns. And they're associated, again, by the bijection we saw before, with these sort of continuous interfaces. What they found in the setting of free probability is that these continuous interfaces appear to minimize a sort of energy integral in much the same way as a soap bubble will minimize the amount of surface area used to enclose a certain amount of volume, or a hanging chain will minimize its gravitational energy. These continuous interfaces associated with continuous Gelfand-Settler patterns appear to minimize a certain energy integral, which gives the interface a certain cost for lying at a certain tilt. And they find this function sigma, which gives a penalty for the interface to lie at a certain tilt, explicitly. So their sigma takes this form here, where this is the sort of penalty for the interface to lie at these angles depicted in this picture here. And they conjecture that there's an underlying reason for this based on the macroscopic behavior of bead processors. Namely that when we take a giant patch of these beads on strings, where the average gap between consecutive beads is p, and we also have a parameter tau there between 0 and 1, controlling the so-called tilt of the configuration, they conjectured that in some sense, the average amount of space or wiggle room per bead behaves like e to the minus sigma p of tau. Or equivalently, if we take a large patch of capital N beads, where the average gap is b and the tilt is tau, then the sort of volume of the configuration should grow exponentially in n, with it should grow like this quantity here to the power capital N. Now, there's been related non-rigorous work suggesting this sort of formula. Some gave an argument based on statistical physics, using arguments surrounding Legendre duality and Lozen's tilings, and in some also non-rigorous work with Neil O'Connell, we used a sort of bootstrapping argument from random matrix theory to guess at this formula, but up to a non-explicit constant there. So we return to the problem we mentioned at the start. We would like some sort of formula for the volumes of bead configurations. So if I have these n strings with k beads on each string, what is the volume of the set of bead configurations? And again, as I mentioned before, if you try and get pen and paper out and tackle it directly, it just seems really hard. There is, however, a technique you can use to gain some insight on this problem. So there's a tool in integrable probability called Cascalin Theory, which has been used to solve various models in statistical physics. So a really simple example, a really simple problem is if you take an n even and you look at the n by n chessboard, of course it has an even number of squares. So it can be covered by these 2 by 1 dominoes. A simple question to ask is, how many different ways are there of tiling this n by n chessboard with 2 by 1 dominoes? Again, if you get pen and paper out and try and look for some sort of pattern, perhaps by induction on the size of the chessboard, it just seems impossible. However, around 50 years ago, a physicist, Kasteleyn, came up with an ingenious way of tackling this problem. So Kasteleyn showed that there's an operator on the chessboard, which can be thought of as sort of an adjacency matrix with a graph associated with the chessboard. And this operator counts the number of domino tilings of the chessboard. There's a clever way of writing this determinant as a sum over cycles and linking up each cycle with a particular tiling of the chessboard, with a particular set of tiles in the chessboard. And again, this operator takes fairly simple forms where you have these intelligently chosen weights that somehow manage to make the signs in all of the permutations here match up with the domino tilings. So the value of this, of course, this is fairly non-explicit at this stage, but we can now appeal to linear algebra to compute this determinant explicitly. We can find eigenvectors, eigenvalues, and since the determinant of the matrix is a determinant of an operator is the product of its eigenvalues, we can write this number of domino tilings as a determinant and in turn as a product. So this formula is particularly remarkable because it's a product of a bunch of terms, none of which are integers. But somehow when you multiply all of these terms together, they conspire to make an integer. So when n equals 6, for example, there are almost 7,000 ways of tiling a 6 by 6 chessboard with 2 by 1 dominoes. So Cascalin theory has been used in other settings. So say we take, you may have seen these pictures before of lozenge tilings, where you have a hexagon and you have these diamond shapes at 3 different possible angles that are depicted in 3 different colors here. And we might wonder how many ways there are of tiling this hexagon using these diamond shapes. Turns out again that there are certain operators on the hexagon with which you can write the number of lozenge tilings as a sum of determinants of these operators. So we come back to our problem. Of course, this problem is continuous. The beads take continuous positions along their strings. And in order to tackle this problem using a Cascalin theory, we need a continuous analog of Cascalin theory. So if you take a bead configuration with n strings and k beads along each string, you can draw a sort of picture like this, where you take any bead in the configuration, jump up to the string above, start traveling along, jump up to the string above, start traveling along, and keep doing this until you get until you've touched at some point all of the beads in the configuration. And we can think of this as a sort of occupation process. So imagine the x-axis here is time, and we have 5 different locations. In this picture, we start off with, we have strings 1, 2, 3, 4, and 5. We start off with someone occupying the first string, someone occupying the third string, and someone occupying the 5th string. And each time you hit a bead, that means you jump to a new string. Yeah, and exactly, and you have a periodic boundary condition. So with this construction, the same number of strings, in this case 3 strings, are occupied at each time slice. So perhaps what isn't so obvious is with every integer n for a number of strings, with every integer k for a number of beads per string, there's a third parameter L controlling the so-called occupation number of the configuration. This occupation number, while it's not obvious, it actually governs the tilt of the configuration. So if the occupation number is L, it tells you that the average of these ratios here is L over N. So we refine the original.
So can you explain again how you do the strings? I didn't understand this. So you draw them from where to where?
So
always to the previous generation?
Yeah, so I start with any bead and I jump up and then I start traveling along. And it's I start again here and then I hit this bead and jump up.
Okay, it's previous.
Yeah, yes, it's periodic both in the horizontal and vertical direction.
You look how many green strips you
have
if you put any, and the maximum.
Exactly, yes. Yeah, so and this parameter L controls the tilt of the configuration. So we can refine the original problem by not just asking what the volume of configurations with n strings, k beads is, but we have this additional parameter L controlling the occupation number. So with this construction here, we can think of these paths here as the sort of cycles of a continuous analog of a determinant, the determinant of an operator on this semi-discrete torus, where we have n copies of the unit interval, which we think of as a torus. And using this idea that these loops are matched up with cycles of a sort of continuous determinant. If we take a generating function for the set of configurations, so this generating function has these parameters t and alpha vary. Of course, it encodes all of the information we would want about w, n, k, l. This generating function can be written as the sum of 4 Fredholm determinants. So a Fredholm determinant is a continuous analog of a determinant. And these Fredholm determinants are operators on this semi-discrete torus. I'll be a bit more explicit on the next slide. That was an informal statement. But it turns out you have these operators here that take this form on the chessboard, where the operator is non-zero, only on neighbouring strings, and it has a sort of exponential term. And it turns out that this generating function is a sum of these Fredholm determinants. I understand I'm throwing a pile of notation at you there, but we'll get a bit more information in the coming slides. So these operators can be diagonalized, and we can write them as a product of eigenvalues. And we obtain this explicit formula for the generating function of bead configurations. And since we have an explicit formula, we can study the coefficients and garner information about these quantities here, W, N, K, L. So we have this kind of main result here, or this main conclusion, that the total Lebesgue measure of configurations on n strings with k beads per string and this perhaps slightly opaque occupation number L is given by this formula here, which isn't the easiest formula in the world to interpret. For some reason, you need to take L different roots of unity, add them together, and then take that to the power of nk. It's not the most transparent formula. However, it is explicit, and this means that we do have an explicit hold on the asymptotic volumes of bead configurations. So by studying the asymptotics of this formula, as n, k, and l tend to infinity, we obtain the following results. So if I take a giant bead configuration with n really long strings of length n, or length order n, and I have n beads along each string, then it turns out that the volume of such configurations grows exponentially in the number of beads, which is n squared in this case. So under a suitable scaling, we have these asymptotics for the volumes of bead configurations. And taking these very rough 1 over n squared logarithmic asymptotics, we obtain this surface tension that was conjectured by Shlyakhtenko and Tao. The surface tension of the bead model, where there's a average gap of p between consecutive beads, and there's an average tilt of tau to the configuration. This surface tension characterizes the amount of space per bead in some suitable sense. So coming back to the pictures we saw at the start, we were interested in these Gelfand-Zetlin patterns, these uniform Gelfand-Zetlin patterns with a fixed bottom row approximating a certain density. When we look at the asymptotics of these patterns, it turns out that the beads shape themselves in such a way so as to maximize all of the room for their bead friends elsewhere in the pattern. When we look at a patch like this, each of the patches sort of has a regular gap and tilt in each patch. We know roughly the volume of each patch, and when we chop it up into patches, it should be the case that these beads macroscopically configure themselves in a way that's the most efficient. It creates the most space. So coming back to this picture, with each patch with this sort of macroscopic Gelfand-Zetlin pattern, we have this continuous interface here. And this interface here, given its fixed diagonal, it likes to lie in a certain way that minimizes the energy, minimizes the cost.
So excuse me, you're running between two different problems, right?
Yeah.
So that finally they are the same?
Yeah.
They're the same.
Exactly, yes. Yeah. So I guess I'll wrap up there. Thank you very much for listening.
Can you explain again where did the volumes of the bead configurations come into play? And you kind of talked about taking like a continuum limits. And where does this happen? I didn't understand.
So this is a formula for the volume. If I take n strings and I've got k beads along each string, and the occupation number is L.
Yeah.
Yeah.
Okay. But so how does this come out of the partition function of the? Yeah.
So how does this come out of that?
Yes.
It turns out, is just a calculation you can do. If you expand this as a power series in capital T and capital alpha, or capital T and e to the minus alpha.
With capital T as well.
It's just a free parameter.
Oh, okay. Okay. This is
the
coefficient of degeneration.
Yeah.
So how did you take the continuum limits?
I'm being quite vague at this point. I'm just saying that. In the work by Shlyakhtenko and Tao, in this setting of free probability, they guessed that if there was a macroscopic formula for the volume of bead configurations, it would be given by the surface tension. So I guess here we're coming at it from the other side. We're computing the volume explicitly and showing that the volume matches. Yeah.
There's no continuum limit happening.
I haven't done the rigorous work on proving the continuum. Yeah.
Have you, so from the physics point of view, like this Cascalin theory is most like you can represent this as partition function of a free scalar Dirac fermion. You notice? Like,
No, sorry.
Okay. Okay, maybe we can talk about this later.
Yeah, great.
More questions? Since there's not, but we can talk about this over lunch.
Great. Thanks.
Okay. Thank you.